Okay, you have to solve problems. Okay,
Mm.
that's your responsibility.
Okay, sir.
Okay, I'll go to the first part today.
Mm.
The first one, introduction. I mentioned it's easy chapter. You should realize that it is easy. Okay.
Mm.
Electricity is
Mm.
flow of charge. So mostly he'll be conducting,
Mm.
considering here, electricity through which medium?
Mm.
Solid, liquid, or gas.
Mm. Mm.
This chapter.
Okay,
Flow,
sir.
no, flow of charge through solid. Okay, basically through the
Um.
conducting wire, which is copper or aluminum, mostly copper, and some components like bulb or something.
Mm.
So basically, so in a solid, the charge is flowing is what?
Mm.
In a
Sir.
solid, in a solid, which charge will flow?
Mm. Um. Positive charge.
No, electron.
Okay.
Okay, basically an atom will be like this, nucleus, and
Ah.
surrounding will be
Ah.
electrons. Okay, if you give a little bit force,
Mm.
this electron will move.
Mm. Ah.
In solid, the atoms are fixed.
Mm.
Copper atom, that is the nucleus,
Mm.
is fixed, but the
Ah.
outermost electrons, two electrons are there,
Mm.
the outermost shell.
Mm.
Okay, so
Ah.
when you apply a electrical potential, this will start moving.
Mm.
Okay, once this
Okay,
thing
sir.
moves here, the next atom, electron, will come and occupy this one.
Mm.
Okay,
Okay, sir.
so basically the electrons are moving. So how fast they are
Mm.
moving, that is basically
Mm.
current.
Mm.
And also how many are moving.
Mm.
Okay, so current is
Mm. Ah. Flow of charge.
flow of charge in divided by time.
Okay.
See, if 5 coulomb charge is flowing,
Mm.
unit of charge is coulomb. Okay, if it is flowing in 1
Ah.
second, then the current is some value.
Mm.
But the same charge, if it takes 2 seconds to flow, then the current is half of it. This is 5 amps. This is
Mm.
2.5 amps.
2.5
Okay.
amps. Okay.
Because it's the same amount of charge, but time taken is more.
Mm.
So how fast the charge is flowing? The amount of charge flowing during
Okay.
the time taken.
Mm.
Okay, one analogy to understand charge flow is water flow. Like
Mm.
you have two containers of water, okay, and
Mm.
you connect it by a pipe, say, okay, water will flow
Mm.
from the one which is higher height to lower height.
Mm.
Okay, similarly, this charge will flow from a higher potential to lower potential.
Okay.
That potential is provided by the battery. Okay, here also, if you want to make this water flow in close, see, this water will come here and get accumulated here, right? But suppose I want
Ah.
to complete a
Yes,
complete
sir.
circuit, I have to push this water.
Mm. Mm.
How do I do it?
Mm.
Pump or motor.
Through
They
pump.
have a pump. Okay,
Okay.
so this
Mm.
they connected to here. If I pump this thing, the water will
Mm.
go here, and from here will
Mm.
come by gravity.
Mm.
Okay, just for pushing
Okay,
up, I
sir.
need a pump. Similarly, this the
Mm.
pump is same as this cell.
Mm.
So the
Mm.
positive charge will get pushed here. After that, it will just drop down.
Mm.
From here to here, it is pushed by the battery.
Batteries.
Okay, so that's why I said analogy flow of water.
Okay.
Current from positive terminal to negative terminal. Um, this
Mm.
current is actually flow of positive charge. It's an imagined flow.
Okay.
Actually, what is flowing is the electrons
Mm.
with negative charge. So the current direction, they are shown like this in this,
Mm.
here it's upward, right?
Mm.
So actually, electrons are flowing
Um.
the opposite direction. Okay,
Um.
so it's equivalent to a positive charge flowing in the opposite direction. It's easy to understand
Mm.
things in terms of positive quantity. So that's why usually we assume positive charge is flowing, even though it's an imaginary
Okay, sir.
positive charge is flowing. That means actually
Oh,
electron is flowing in the opposite direction.
okay.
Okay.
So positive charges always moves in a opposite direction, sir.
Yeah. Actually, there are no positive
Um.
charges. Suppose there was something like a particle which is got same mass as the electron, but sign is opposite. Okay. It will be some
Okay.
current, right? The same current will be produced by an electron moving in the opposite direction. The positive thing is moving in the upward direction. The is equivalent to electron moving in the opposite direction. So
Okay.
here the current is this way. That means positive charge is flowing this way, or you can say positive electrons. It's an imaginary concept, but actually electrons are moving in the opposite direction. Electrons are moving this way. Okay. And SI unit of charge is Coulomb. Okay.
Coulomb.
SI unit of time is second. And current
Seconds.
is charge by time. How fast the charge is flowing. So it's Q by
The
T.
current.
Current I is the amount of charge flowing in the time T. Okay. So this is in coulombs. Now this in second. And the unit for current is ampere. So ampere is coulomb per second. So instead of writing 1 coulomb per second, the short form is this one, 1 ampere.
Okay, sir.
Okay. This solved problem. 1 coulomb flows through bulb in 5 seconds. Current through the bulb. So current is charge that's flowing, it's 2 coulomb. Divided by the time it takes 5 seconds. It's coulomb per second, which is same as ampere. So 12 by 5 is same as 24 by 10, 2.4.
2.4.
Okay, and obviously when you're drawing a bulb, you just put a sort of cartoon diagram, not the actual bulb. Even the actual coil will look like this. In the lab, you might have seen. Or it could look like this carbon resistor. There'll be some color code. But in circuit diagram, just mention this as a zigzag line. That is resistance. So for resistor, it's zigzag line. Variable distance, you just have to put a arrow mark. Or you can also represent this. The contact current will come here. This much of resistance will flow, and the current will go like this. So the thing contact point is moved here means more resistance is included.
Okay.
Because current will here it cannot flow because it's open. Only this part will flow. So if this contact point is moved here means it will go through larger resistance.
Oh, okay.
So this is basically a rheostat where the contact point move the see. So same thing if you put an arrow mark, it means it's variable. Ammeter for measuring current is a circle with the A symbol. Measuring current. Okay. Voltmeter is voltage is the one that will drive the current. Like this pump is going to create that energy, right? Similarly, the cell will create the energy for the charge to flow. That E potential or potential difference. Galvanometer is for measuring the current. Actually, galvanometer is a sensitive instrument. Say it will measure to a maximum of say 0.1 amps, just for example. But suppose you want to make it to measure up to 1 amps, you have to convert this galvanometer to ammeter. Okay, so actually ammeter is galvanometer with some modification so that it will handle higher current. So you call a
And galvanometer handles lower values.
Yeah.
Okay.
Diode, it's like this. Light emitting diode means just this diode. You just have to show that light is coming out. These two arrow marks show the light coming out. Light emitting diode. Okay. So it's going to emit light. Ground connection means I can have a reference potential at 0 volts. See, even if a cell is like this, 5 volts, it means that the difference from here to here is 5. So, but if I make this thing 0, then it is 5 volts. If you make this thing 1 volt, then it is 6 volts. The difference is the one which is the given by the cell. Okay.
Mm.
Suppose I make this as 0 to represent it, I'll just put a earth connection. So if this thing is 0 volts.
Okay.
Reference point for potential. Direction of current flow is opposite to the flow of electrons. Because by definition, current is the amount of positive charge flowing in the per second. Same effect I can produce by having a negative charge flowing in the opposite direction.
Okay.
Like water will flow from higher height to lower height. Similarly, the electric charge will flow from higher potential to lower potential. So,
low potential.
Yeah, in this circuit, sure, the battery is there, no, and they have put this as plus. That means this is at higher potential. So the positive charge will move in this direction. Okay, and then it will come here and then come here. Here it is going in the negative to positive, that is done by the cell. The positive charge will come here and stop here, no? Why will it? It will get a negative plate. So some force has to push it to the positive plate. That is done by the cell. See here, see from here to here, it's higher potential to lower potential. Here also to here. But from here to here, it's lower potential to higher potential. Which is done by the cell. So other than the cell and other parts, it's charged from a higher potential to lower potential. It is same as this water flow. See, at this point, it's from higher height to lower height. But here it is from lower height to higher height. That's done by the pump.
Pump.
Okay. So similarly, if you leave this, what is happening inside the cell, in other parts, it will be like current flows from higher potential to lower potential.
Lower potential.
Okay. Suppose there is a charge here, Q, and the potential due to this charge at this point. So what I will do is, suppose I take another unit charge, 1 coulomb. Okay. Assume this is positive charge. What is the force on this 1 coulomb charge? Which direction? It's towards
opposite
right.
Direction.
It will be towards right. Why? Repulsive force, no?
It flows up.
Two positive charges in repulsive force. That you have studied or not? Charge.
Yes, sir.
So positive and negative means they'll attract.
Same signs will be repelling.
So this is plus Q. I mean, I said it's positive, and I have 1 plus coulomb here. So there will be repulsive force. So to bring this charge nearby, I have to push it. There has to be external force to push this thing towards this one, right? So when this 1 coulomb, when it's a very large distance, say infinity, what is the force on this one? It will be approximately 0, because force is inversely proportional to distance square. So force due to the charge is inversely proportional to the distance square. So as you keep going far away and away, obviously going away from the source, the effect will be less, right?
Yes, sir.
So as you go to infinity, that's the limit. So 0. So to bring this charge from infinity to the thing, some amount of work you have done, W. Okay. So that work done to bring unit charge from infinity to this thing is called potential at point B.
Okay.
Okay. Similarly, if you have a point C, then the work done to move from infinity to this thing is potential at point C.
And by C.
And you can figure out that VC is greater than VB. Because more work is required to bring this thing here, because I'm still coming
push
close. So from infinity to this one, if the work done is say 5 Newton. From infinity to this one will be more than 5. For example, 7. Right? Because I have to do further work. After coming to me, I
Yes,
still
sir.
have to move inside. Okay. So as I come closer, the potential will keep on increasing because work done is more. But I can find the work done to move from B to A, B to C.
Yeah.
That is how much?
B to C is 7.
7 is from infinity to C. That is the definition of potential at point C.
Okay.
Okay. And potential at point B is 5 volts. Sorry, some
5
B.
volts.
That's equal to 5 because it's 5 Newton work. Okay. So the work done to move from B to C is 2 newtons.
2 newtons.
Okay. So potential difference between point B and C
Will
is
be
the
2.
work done to move 1 coulomb charge from B to C. So from the concept of potential, I have moved to the concept of potential difference between 2 points.
Difference.
Okay. Potential point is work done to move from infinity to that point. But now I want to work done to move from point B to point C.
Point 2.
So that is the work done to move from here to here minus the work done to move from here to
It's infinity.
up to
C is infinity.
Yeah. What's C?
Okay.
Starting point.
Starting.
Okay. So potential difference is work done to move from potential difference between say point 1 and 2. Okay. It work done to move from 1 to 2. 1 and actually it's 1 to 2 means work done to move from the opposite direction 2 to 1. See potential difference if they call this as V1 minus V2. So that means V1 is nearby. The second point is far away to the source charge. Okay. Use point 1. So that means the work done to move from 2 to 1.
Okay.
Look at the charge. If the work done to move 1 coulomb charge is 5 joules, okay, the work done to move 2 coulomb charge will be how much? Just common sense.
10 joules.
10 joules. Okay, so the work done to move Q coulombs will be Q times 5.
5.
Okay, so the work done to move 1 coulomb will be Q times 5 divided by the charge Q.
Charge.
That's why the work done to move whatever is the amount of charge we're moving divided with the charge value. This is work done to move charge Q, not 1 coulomb. From that, I can get the work done to move 1 coulomb by dividing this thing by Q. Okay, so this is the definition of potential difference. Potential is potential.
The distance between those.
They are said just by words, but they are not mentioned it. So same way, if you have to give potential in terms of this equation, potential V at a point is work done, move from infinity to that point P, and say potential at point P, divided by the charge. Understood? No. This potential at point
Yes,
P.
sir.
This potential difference between point 1 and 2. So I'm moving from say 2 to 1. So it's 2 to 1. And one a bit higher potential. It's V1 2. Here it's 1 2. Here it's 2 1.
Okay.
Okay. If VA is higher than VB, VA means VB. Okay. If VB is higher than VB, it's, and then you have to remember that B is at higher potential.
Okay.
Here A is high potential. So potential difference is 1 volt. So potential difference, I can call it PD, is the work done divided with the amount of charge.
By charge.
Work done by charge. Okay. So work done unit of work done is how much? I mean, what? SI units?
Volt.
Work done is joules. Force is Newton.
Okay.
Force is Newton. Newton into distance is work done. And the short form of this one is joule.
Okay.
Okay. Instead of writing Newton meters, convenient to write one symbol. No. So Newton meter combined as joule. Similarly here, work done is joules, and the unit for the charge is coulomb. So instead of writing joule per coulomb, I can have a single, unit, and I call it volt.
Okay.
So if I have 1 joule by 1 coulomb, that's 1 volt.
1 volt. Okay.
So potential difference of 1 volt is if 1 joule of work is done
1 joule
in moving 1 coulomb of charge from one point to another, because he's talking about difference. Difference is moving from one point to another. Difference potential means from infinity to that point.
Infinity to the starting point.
Now, if it is potential difference means between the 2 points which you are considering.
Okay.
So work done moving 10 coulombs across 2 points in a circle is 10 joules. What is the potential difference between the 2 points? Just do this one.
Let me calculate.
Get the answer.
Yes, sir. 10 volts, sir.
Potential difference is work done divided by the charge.
Work done divided by the charge. So which is 100 by 10, and then it's 10 volts.
What is the unit?
Volts, sir.
Volts. Which is same as joule by coulomb.
Joule by coulomb.
Okay. Ohm's law. So if you have a resistor and connector, obviously once you have a resistor, I need something to push the charge, right? That is the battery.
Batteries.
Okay. And you have this rheostat. What is the purpose of this rheostat?
Rheostat.
See, suppose this resistance is small, say R. Okay. The current flowing in the circuit will be whatever is the potential here, V by R. Because this V will come here.
Yes, sir.
Okay.
So the
and if this R is small, the current will be very high. Suppose I have this rheostat of resistance R, then the current will become V divided by R plus R.
R plus 1.
Because the same, now the V will not be here. It will be V1, and the drop here will be V2. And then V1 plus V2 VT. Okay, because the drop is getting distributed between R and this rheostat. So to protect this, any circuit, you will have a rheostat to protect the, in the beginning, we'll put the rheostat to have a large resistance, to be safe. There is large amount of current to flow. And once you know that current is not flowing much, then you can decrease the resistance value. Okay.
Through rheostat.
No. Rheostat can be there. Still some amount of resistance is there, no?
Yes.
Okay. Because of this R value, if the R value is large, means you don't need this rheostat. You can cut this thing fully. Suppose this R value is small, means you need at least some amount of resistance here. Otherwise, the current will shoot up. Okay. So for this fixed rheostat position, if I increase V, this rheostat is fixed. R is also fixed. So when I increase I will also increase.
I will also.
Because basically
because it's directly proportional to it.
Okay. So if we plot this I value versus the V value, I get points like this. And if this potential is 0 volts, means same as cell not being, then the current will not flow. So 0, 0 is a point. So after that, increase the current. When I increase the voltage, the current increases. So that is called Ohm's law.
Okay.
Here.
Okay, sir.
When I increase the voltage, the current will increase. And current is on the y-axis because what we have in the control is the voltage source.
Voltage.
Because what we have is a voltage source. Here, one more purpose of rheostat is by controlling this resist. See here, even if this V value is fixed, if by adjusting this one, V1 can change.
Okay.
Actually, this is V1, the voltage across the resistance. Okay. V1 versus I. So if I increase this resistance value, V1 will go down.
Okay.
So to increase this
Are
V,
they inversely proportional, sir?
not directly proportional. See, if I want more resistance voltage drop here, R should be increased, or the rheostat value should be decreased.
Decreased.
Okay, so
Okay, sir.
So first this point, if you have to get the second, more current has to flow. Further, I have to decrease the R value, rheostat value. So here, rheostat is less resistance. Here it is more, comparatively more. V is fixed. To get this variable, I'll adjust this rheostat. So this is actually V1. Okay. It's potential drop across the resistor. So this is a straight line relation. And the slope of this line is what? 1 by R.
1 by R.
Because slope is Y by X or
delta. Y by X.
Delta by the difference. Here, what's there in the y-axis is the current.
Current and the x-axis is volt.
Resistance is V by I. So 1 by I by V is 1 by R. So slope is 1 by R. So if you have for this resistance, this is the line, and the second distance say R2 or small R2. This is the line. This means R2 is which one is more? R1 and R2? Which one is more?
R1.
R1 is more. Okay. There is another way to understand for the same voltage, the current of R1 is sorry. No, R1 is more. So current in R1 is less, current in R2 is more. So R2 is resistance.
Okay.
Correct. Given voltage value, you can check the current. Current is less resistance. So R2 is less.
Okay.
Resistance of a material. Resistance basically, so even if this is a copper wire, the electron here will go and collide with the copper atom. Basically, it will have a zigzag motion. Okay. It can also go like this, but it will go like this effectively. Okay. So this is sort of a resistance. Yeah. So it depends on the material also. So this amount of resistance depends. Okay. One more thing is, if it has to go through this much length, the resistance will be also. So if I increase the length, then the resistance will go up.
Increase.
Because I have to cross through more difficulty. See, if the length is up, I have to spend some energy to come up to this point, right? If the length is increased, means I have to still have this much extra difficulty. So resistance is more. So R is proportional to length. But the area is more, then it's easy for the thing to flow because I have multiple paths. So it's inversely proportional to the area.
Okay.
So these two can combine and write as R is proportional to L by A.
L by.
Constant of proportion is called resistivity, rho into E by. This depends on the material. So copper will have one value, aluminum will have another value. So two wires of same L and A, same energy, but one will be of say copper, other will be of say aluminum. So R copper and R aluminum will be different because of the difference in the rho. Okay, and rho copper is less compared to aluminum. I think so. Okay, whichever has got less rho will have less resistance. Even the length and area will match. So calculate this connector. This is different. This is Ohm's law. Okay, still he has not come to this. Here only here. Here resistivity. R is proportional to the length. If the length is more, means you have to pass a greater difficulty. So distance will increase. If area moves, it's easy to fit because I have more parts. More parts. Like if there is a narrow road, it's easy for the traffic to flow, right? But the road is long.
Yes, sir.
The distance between the 2 points is starting from A and reaching B.
Mm.
If the distance is moving, so obviously you spend more fuel. Okay,
Yes, sir.
that is same as resistance is more. So resistance is proportional to the length, but inversely proportional to the area. So you can combine and write like this, and the constant of proportionality is rho.
L by A.
Yeah.
Okay.
This same thing you can cross multiply. Okay.
Okay.
So in some sense, you can say if you take a material of length 1 meter and the cross section area is say SI units, so 1 meter square. In this case, R will be same as rho. Why is that so?
Because the resistance are directly proportional to the length.
Into L by A, so 1 by 1. That is same.
L by A.
So that's how resistivity you can understand like this. Defined as resistance of unit length of unit area of cross section. Resistance of conductor of unit length of area of cross section. Even if the length is say 2 meter and the cross section area is 2 meters square, for this also resistance is same as rho.
Rho.
Because rho into 2 by 2, right?
Yes, sir.
But this is simple way of defining. Instead of 2, it's 1 is easy, That's why it's defined in terms of 1. So that's why I just put unit length. So reciprocal resistance I can define as conductance. Okay. Once I know resistance, I can just have to take the reciprocal. That will give me conductance. And resistivity symbol is rho. I can also take the reciprocal of it 1 by rho. That is called conductivity. So resistance and the conductance are opposite, right? If conductance more means it's easy to flow. Resistance more is difficult to flow. So there should be a reciprocal relation. Right? Because when the rho is less, G will be more. Similarly, resistivity rho is less means conductivity sigma will be more. Okay. And resistance unit is what? R is V by I. So volt by ampere. So this volt, unit of resistance, you can say volt by ampere, but this I can have a short notation as ohm. And the symbol is omega. And conductance G is 1 by R. So the unit is 1 by ohms. Okay. And if I write this in the reverse order, it will be MHO. Have they used that thing? They used it. Ohm you write in the reverse order is reciprocal, no? So they have put more. Okay. Conductivity, it's ohm meter in R equal to rho L by A. Rho L by A. So R into A by L is rho. So this is ohm and area is, so ohm meter is unit for resistivity.
Yes, sir.
Okay. So conductivity is reciprocal. This will be mho per meter.
Per meter.
Okay. Meter I cannot write in the reverse order. It's just in one letter. So just put it as m raised to the minus 1. 1 by meter. So the first part I said the one thing that needs to be explained is this potential difference or the concept of potential, the work done to move infinity. So the difference between these two is the
infinity to the starting point.
Yeah. So this one and also this resistivity concept. If we take a wire of length unit and cross area of 1 meter square, resistivity same as the resistance.
Okay.
Because this is the formula. In this, if I put L and A as equal, R and rho will be same. So simplest thing to put is 1 meter and 1 meter square. I can also put 2 meter and 2 meter square, but that will be same. But For definition, use the simplest one.
Okay, sir.
That's why you define as unit length or unit area of cross section.
Okay.
It's the resistance of that conductor.
Mm.
So yesterday or the last time we did combination of resistors, right? So this one,
Yes, sir.
you know how to simplify, right?
Yes, sir.
R1 and R2, how will you simplify? They are series or parallel.
So
R1 and R2,
they are series, sir.
series means current should flow, right? Same current should flow. The current here, the current here and the current here could be different. Suppose this current is say 5 amps. Suppose R1 is less
They are
than,
parallel, sir.
they are parallel because potential is same. Drop from here to here, if it is V1, V2, V1 and V2 will be same because it's same point, no? So these two are parallel. So the combination, if we call it RS1, okay, these two I'll call it as RS3 or RS2, whatever.
3.
Okay, they have put 2 only. Okay, RS2. And these two are in series. So if I add these two, I'll get the total resistance RP.
RP.
This is a different question. This one. The first one you're combining, obviously should be called P.
The
Parallel, no? These are in parallel, so RP1 and RP2, and then the combinations in 1 and 2 parallel, get the value. 3 and 4 in parallel, get the value. Okay.
Value, and we need to add those RP1 and RP2.
Yeah. After doing this, take the reciprocal to get RP1. This is 1 by RP1.
Yes, sir.
Now this is same, but it's opposite to this one. Here these two are in series.
Opposite.
Two are in series. So combine this as
They're
combine this as 1. After these two are in parallel. So RS1,
yes, sir.
R1 plus R2, and RS2 is this one. After that, you have to combine as a parallel one.
RS plus R1.
Okay.
Yes.
So the region after